All right, we're on page 7 in your white packet, so go ahead and turn to page 7. It talks about 7 higher degree polynomials. So we're exploring what happens when, instead of just being a second degree equation like a parabola, you have a bigger degree like 3. Again, this is the drawing that went with that box problem that we've been working on. This was the 30 by 30 piece of paper that we're folding up, creating the equation. And this is what the equation ends up looking like in general form. I think yesterday we looked at it in factored form. It was 30 minus 2x squared times x. If you expand it, you end up with this 4x cubed minus 120x squared plus 900x. So if you wanted to FOIL that out and then distribute the x, you should get that equation. So that's one of the things that you're going to be doing in 7.6 and 7.7 is taking polynomials in factored form and FOILing them and writing them out in general form. Okay, here is the graph. We explored it a little bit yesterday. The maximum volume was a 2,000 cubic inch box with height 5 units or 5 inches. And one thing we noticed yesterday was that it bounces off here at 15, 0. Okay, it bounces off the x-axis, and that's known as a double root. That occurs, it has that action there where it bounces off the x-axis when you have one of the roots, like this, one of the factors being squared. See how the 30 minus 2x is squared? That's what creates this sort of parabola-like effect where it bounces off the axis instead of cutting through it. Okay? So that's a little bit about what the graph might look like of the polynomial when you have a double root. Next, let's look at example A. They basically just lay out everything for you, and you have to write the equation. Find a polynomial function whose graph has x-intercepts 3, 5, and -4. So that means 3 is a root, 5 is a root, and -4 is a root. So we'll call this root 1, root 2, root 3. And we also know the y-intercept is 180. That's going to come into play a little bit later. So in factored form, we have how many roots? 3. So we need an R1, an R2, and an R3. Start there. Next, leave the A in place, but change root 1 so that it says x minus 3. The next one will say x minus 5. And the last one will say x minus -4, more commonly known as what? X plus 4. So those are the 3 roots. Now it's time to bring the y-intercept into play. There's always another little bit of information that you need in order to figure out what the dilation is, okay? And that is usually the y-intercept. What it means is when y is 180, so we're replacing y with 180, x is 0. Well, if x was 0, 0 minus 3 would be 0 minus 5, 0 plus 4, 4. So we have -3 times -5, that's 15, times 4. 15 times 4 is 60. So all of this is 60. A equals 180. And when you divide both sides by 60, A must be 3. So A is 3. We're going to graph it and describe the features of the graph. So what we're going to graph is 3 times x minus 3 times x minus 5 times x plus 4. Here we are at the calculator. You can see in the y equals screen I have the equation that we're graphing. I also have the window that we're using. Make note of that. And let's go ahead and hit graph, and we should see this polynomial. So it cuts up past -4. You can see it comes back down, hits a y-intercept. If you hit trace, it usually pops up right on the y-intercept. Trace. There it is, 0, 180, just like we thought. You might want to trace to -4. See how it says -4, 0? Good shape. 3 was another 0. 5 was another 0. You could do other things here. Maybe you want to make the window a little bit taller and a little bit lower so that you can see the what and what? The maximum and minimum. Now, these are known as local maximums and minimums. I'll explain why in a minute. Let's make our y-min go down to -50. Let's just expand this a little bit. Let's make our y-max go up to 300. Graphs have things known as absolute maximums and minimums and local maximums and minimums. The comparison might be to the highest point in Allegheny County versus the highest point in the United States. Are they the same? No. But locally, around here, we have a highest point. It's somewhere, I think, out in Robinson. Okay? Don't quote me on that, even though now I'm on video, so great. What if I'm wrong? Anyway, okay, let's say the highest point in the United States is Mount, do you know? Mount McKinley, thank you, in Alaska, right? Is that the highest point on Earth? No. But locally, in Alaska, it certainly is the highest point. So this right here is what we call a local maximum. You could find that. You could find this local minimum. It's not the overall max or min, but it's relative to the things around it. The last thing that I wanted to talk about was the end behavior. You would say that this graph is increasing at the beginning and increasing at the end. That's how you describe its end behavior. Overall, what is this graph doing? Is it increasing or decreasing overall? It starts down here and goes up, down, up. So what's the overall effect? Increasing. That was because our A was positive 3. If the A would have been negative, it would have flipped the whole thing upside down. Thank you. That's all.